So we're talking about electron configurations. And we're talking about, on your POGIL, on the Cracking the Periodic Code POGIL, the fact that we've got sometimes where the configurations don't follow the pattern I taught you, right? So, for example, let's use chromium, which is here in period 4. It's number 24. If we were doing the shorthand, it would be argon 4s2 and then 3d4. We cool with that? Or if we were doing copper, which is in that same period, it's number 29, it would be, again, argon 4s2 3d9. Are you with me? But what we find when we actually do the experiments is that that's not correct. Even though it follows the pattern we taught you, it's not actually correct. What we find is that actually their configuration is 4s1 3d5 for chromium. For copper, it's argon 4s1 3d10. And you say, wait, what? Why would that do it that way? I'm going to push you back again on that POGIL to the very back page that showed you that electron energy level diagram that shows you how they fill up. What it's telling you is that in that 3D sublevel, you see that diagram has got these 5 boxes like this. You remember when we talked about energy levels being like hotels, and each energy level is a floor of the hotel? It's like the 3D floor actually has 5 rooms in it. Because D can hold how many electrons? 10, right? So it's like it has 5 rooms. And what they prefer to do is to put 1 electron in each room first. Just like if you're traveling with a whole group of people, right? You prefer to have your own room. You'll only double up if you have to, right? So if I've only got 5 electrons, we're going to put 1 in each room, and I'm happy. So what happens here is, because this 3D level only has 4 electrons with chromium, it actually is more stable. It takes less energy to take one of these from 4s and put it into 3D. So that way, every room has 1 electron in it. Does that make sense? It takes less energy and is more stable. That's the key, that term right there. Because that's what electrons are all about. I just want to be stable. Atoms want to be stable. Yes, ma'am?
So it would be, if you filled up the S and left the D, unfilled would be more unstable?
It would be less stable than to go ahead and fill up each one of these rooms in that 3D sublevel. You're correct. Yes, sir? It could, certainly, but certainly for chromium and for copper, these 2 exceptions I'm showing you, it's going to end up like this. It's going to end up the 4s1 3d5 or 4s1 3d10 consistently. Sir?
So is that what the POGIL means when it says the 2 configurations?
Right. What we actually have found through observation, through experiment, is that these are correct.
That means lower potential energy for the second.
Right, it means it's more stable. Yep. More stable, it takes less energy to fill up that 3D first instead of filling up 4S. Yes?
How do we know when it does it?
It's a great question. Because truthfully, and I'll get you in a second, Lucas, if you looked at the actual configuration for the periodic table, for every element, this happens probably 25 times. Okay? But I don't expect you to know them. I do expect you to know these 2 exceptions. Okay? So on a test, even if I gave you an element that doesn't follow the pattern, I would want you to write the electron configuration like I taught you. Does that make sense? But for these 2, I want you to write the exceptions. Yes, ma'am.
These two elements, or
Right, these two elements, chromium and copper. Yep. Those are the only two exceptions that I expect you to give me the red one, not the black one. Sir?
Question.
Yep.
Okay, so this is you getting it shorthand, right? Would
Yes.
it happen the same thing if we do it like
Sure, you would just do all the stuff that gets you up to argon, right? 1s2, 2s2, 2p6, 3s2, 3p6, and then now we're there. Cool. Lucas, did I answer your question?
How do we see these different
So it used to be, your textbook used to have a whole list of them, but this newer textbook, they took that out. So for every element on Wikipedia or any place on the internet, you can go and find it. It'll show you the electron configuration.
I don't know, but I meant how do we observe these individual electrons?
Yes. You're asking a good question that is deeper than I want to go right now. Basically, through experimentation, based on how things react together, we can say, oh yeah, this is coming from here and coming from there. Let's talk more. I can give you some more information.
So we should use, we could get those answers for doing long,
Sure, exactly. For longhand, you'll have all the other pieces other than argon, and this will just be the end. 4s1, 3d5. Just for these two is all I want you to know. It happens more often, but you only have to know these two. Sir? There really are no significant amounts of chromium who follow the black pattern. They all follow the red pattern. So there could theoretically be some differences in how they work and how they react, but again, for the most part, they're staying like the red. They're not going like the black. Are you with me, friends? Whew. Okay, good. Yes, sir.
Can we go over the hint questions too?
The what?
For number 22, there's like options just hint two questions.
Right, no, all they wanted to know is that it takes less energy, right, and it's more stable. That's your answer for number 22. That's why they do it. Because we're filling up that 5D, sorry, the 3D with the 5. And of course, for copper, I didn't mention this, but are you comfortable? For copper, it just puts 2 in each room, right? So that fills up that 3D completely for copper. Don't worry about the questions that are written there. Just so you understand the why of that. It's more stable and takes less energy to put the electrons there. Okay. The last piece I want to get at you with this conversation is about the article that you read that was on the periodic table. And it was a toughie, right? It was a big, this is probably last week sometime I assigned this to you. This is a college level paper, right? 2 pages, so not very much, or a page and a half actually. And they were arguing over where lanthanum and actinium should go on the periodic table. Right? Lanthanum and actinium are the first, they're in group 3 here on our table, right? But some tables, they actually put them down here in the inner transition elements. I was looking at Mrs. Serrano over for her integrated science class. The periodic table that she was using from the book that she was using had lanthanum and actinium down in that 4F, 4 and 5F. And then these guys on the end, lutetium and lawrencium, get pushed up into the D column. And there's a big conversation between chemists as to why they should stay or they should go. Do you remember any of the arguments why they should be one place versus the other? If you wanted to go to school, see, this is there, right? I'm talking about this. Oops. I'm talking about the article here. Read the attached article, right? This article. Lanthanum and actinium should remain in the D block. I think you can see where this author wants us to go, right? He's saying, no, they should stay up here in group 3. Do you remember any reasons why? Well, let me ask you this. Why should any element be in a certain group? What's so special about groups of elements? Yes, sir? They have common properties, common attributes, he said. Absolutely. So a good question would be, does lanthanum and actinium have properties that are similar to scandium and yttrium, which are in that third group? Or do they have properties that are more like these guys? And the answer is more like group 3. They fit better there. Yes, ma'am?
So, when you're talking about like similarities in some of the groups, but
Yes.
to F, is it all of that?
Right. These guys tend to have similar properties as a group, yes. That's why we kind of also put them on their own little space there, those rare earth elements, yeah. Anything else it said? Do you not remember? Or can't have understood? We also know that lanthanum and actinium, if I was just going to lanthanum, so let's do lanthanum as a electron configuration. So lanthanum is right here in period 6. So my noble gas is xenon. So Xe, and then what comes next after xenon? 6s2. And then now I'm just here to lanthanum. So what would you write there? 5d1, right? How some folks would write that would be 4f1. And they're saying, okay, which one? This goes back to what Lucas and I were talking about, right? How do they know? Well, when they do the actual experiments, they find that this is not correct. 5d1 is where that electron goes. So this author argues, why should we put them down here? Because the electron goes here. Does that make sense? What's that? Right, so these guys on the end, so let's do that one. Lutetium, how I would do lutetium, which is way down here on the very end of 4F, right? So again, same noble gas, xenon. Let's erase this so it's not in our way. Xenon, 6s2. Anybody? 4f 14 and 5d1, because we can't forget about lanthanum, right? So here's what I'm telling you, and then I'll answer your question. 1 second, Abby. Here's what I'm telling you. I want you to always count lanthanum in that 5d. Does that make sense? I want you always to put lanthanum in 5d. I want you to always put actinium in 6d. Even though, and here's the funky thing, even though sometimes the electron will go into 4f, sometimes it'll go into 5d. It depends on the element that you're dealing with. It goes literally almost back and forth. I don't want you to have to fuss with that. Again, in a college level or in a graduate level class, they'll expect you to know all the different ins and outs. For our sake, I want you just to count them always as part of the D sublevel. Does that make sense? Even if I stop somewhere, let's say I was going to europium here, right in the middle of 4F, I would still write 4F, 1, 2, 3, 4, 5, 6, 4F6, and then put 5D1. Yes, ma'am? You could. I put it here because we filled up this one. I'd be okay either way. I'd be okay either way. Abby, thanks.
Why don't they put 5D and then 4?
I put it on the end because if we continue on in the 5D, let's say we were going to tungsten, which is further along in that 5F, I wouldn't want you to write 6S2, 5D1, 4F14, and then 5D3 again. Does that make sense? I'd rather you write 5D4, put all the D's in one piece. So that's why I just put them all together, put them on the end.
Okay, so for example, what you're saying, right, if we go to PM and
Promethium,
I would still end up always putting 5D1 at the end.
Yeah, you would. Yep.
Okay.
It would be 4F4 and 5D1.
So for the two bottom columns, I'd always put 5 1 above.
Right, or if you're in the bottom row, if you're in the 5F, it would be 6D1 for actinium. Sir?
So the bottom two rows, transition?
Inner transition elements.
Do they have groups?
They do not, because remember, this is like a drop-down menu that gets squished in between group 3 and group 4.
So they have rows but not groups.
Right. Right. Are you with me, my friends? Because again, I will give you on the test one of these F guys to write. I will give you one of the D guys to write, definitely, where you have to go past the F block. I promise you. You'll see it. So I just want you to know how you're going to write those. Another example, Marlon? Okay, as I say, you're looking a little nervous. Okay, pick me any of these guys down here. Just from either the F or from the D or from even the P over here. You can do 6P as well. That's all right. What do you got, Marlon? What do you think? Dubnium, which one is that? 105. That's hafnium. Or honium, excuse me, not hafnium. 105, is that what you want? Oh, maybe they switched to the name. Let's just make sure. Yeah. Dubnium. Interesting. Very good. All right, so we'll go that's DB. Is that correct?
Yes.
DB. So DB, which is number 105. Okay. So what's my noble gas? Radon. Okay, and then after radon, what comes next? 7S2. Okay, so that takes francium and radium. Now I drop down into the Fs. 5F14. I'm going to fill it all up. That takes me all the way through Lawrencium. And then pop back up here. But don't forget about actinium, right? So it'll be 6D, how many? 6D3. And remember, friends, remember, you can always add up the numbers. So what's radon's atomic number? 86 plus 2 plus 14 plus 3. You add that together, you get 105. Which again, that is this number. That's always the way you can check your work.
That's how you always write the ones that have the F.
Yes. If you stopped, let's say you weren't going all the way through the 5F, but you stopped, let's say 5F3, you would put 6D1 to count for actinium on the very end. Because we don't want to forget about this guy here. Okay? Whew. Are you with me, my friends? Another one? One more? How about one more? All right, let's have you do polonium, which is number 84. PO, number 84. Try it. I'm not going to talk. You try it. And again, that periodic table is right in the back of your textbook. Shorthand, please. Guacamole. That would be a humongous long. I'll give you two. Sorry. Thanks. I'm passing you out the study guide. I thought I had given these to you once before, but they've been on Schoology for a couple weeks now. I thought I did, but Just in case. Perfect. Okay, we ready? All right, polonium, what's my noble gas? Xenon. And then? 6s2. 4f14. 5d10. And 6p4. Is she right? 6p4? Cool. Absolutely correct. Are you with me, my friends? Okay. I'm going to stop my recording.